Well, welcome everybody to podcast number 3, where we're going to calculate the equilibria constant, and we're going to start to get an understanding for what it actually means, right? Right now we know it's like products divided by reactants, but you know what? Like, what does a big value for K mean versus a small value and stuff like that? What does this actually stand for, since it doesn't have any units? We're going to figure that out in this podcast. If we want to calculate our value for our equilibria constant, right, one way that we can do it is by taking the equilibria pressures and just plugging them straight into our expression for K. Right, this is easy. If we know every species at equilibria already, all we're doing is plugging numbers in and then typing them into our calculator and spitting out a value. The other way to do it, which is more complicated, right, is to take the original pressures and then see what happens over time until we finally reach equilibria. Right, it says we're going to algebraically link them to this. What we're going to see is that, over time, we're going to look at the coefficients from our balanced chemical equations, and we're going to use them to figure out when things are going up and down and by how much. And then we can plug those in to solve for our equilibria constant. Well, let's work a sample problem where we are going to take some ammonium hydrogen sulfide, and it's going to come to equilibria with some ammonia and some hydrogen sulfide gas. All right, it says that we have some ammonia, hydrogen sulfide, ammonia, and stuff like that in our flask, and it says when equilibria is established, it is found that the partial pressure of ammonia has increased by 12.4%. We want to calculate K for this. Okay, so what we're going to do here first, right, and this is very difficult. This is probably a little bit more difficult problem than we might see right off the bat, but the first thing I'm going to do here is find the change in pressure of ammonia. All right, and the reason I'm going to do that is because that's going to let me figure out then all of our equilibria values of things. So let's find the change in pressure for the ammonia. All right, well, the ammonia, notice that we started with 0.692 atmospheres of ammonia. All right, and it says that the partial pressure of ammonia has increased by 12.4%. So I'm going to take that value and multiply it by 0.124. And we're going to get a change in this of being 0.0858 atmospheres. All right, now it says we're going to set up an ice table to determine our equilibria pressures. All right, an ice table stands for initial. And if we haven't done ice tables before, we're going to do the heck out of ice tables in this next few chapters. So we're going to get really used to seeing them. Initial change, and then E is equilibria. All right, and so equilibria is what we want on all of these problems. All right, now when I set up an ice table, what I like to do is I like to write in my equation. So I've got my NH4HS solid, my NH3 gas, and my H2S gas. I'm going to put my little arrows in there just to remind myself what is a reactant and what's a product, because those come in to play a little bit later on. All right, now, right, the initial amount of my ammonium hydrogen sulfide, well, we had 10 grams, but notice that this is a solid, right? So I don't really care about solid. So realistically, I don't care about this column whatsoever, because it's not going to show up in my equilibria constant expression. Now, I do care about the ammonia and the hydrogen sulfide. So the initial amount of ammonia was 0.692 atmospheres. That was given to us in the problem. And the hydrogen sulfide was 0.0532 atmospheres. Again, that's given to us in the problem. All right, now why did I do that change in pressure of ammonia? Because that can now go in here, as this is going to go up, right? Because we're increasing by that 12.4%, we're increasing by 0.0858 atmospheres. Okay, now you might be tempted to increase the H2S by 12.4% of it. It does not increase by 12.4% of it. It is going to go up by the same amount as the ammonia because they are both going up right by, say, each time the solid decomposes, we're making 1 mole of ammonia and 1 mole of our, this is a terrible one all of a sudden, 1 mole of our H2S. So if I made 1 mole of ammonia, I'd make 1 mole of H2S. Well, remember that moles and pressure are directly related. And so if the pressure of ammonia goes up by 0.0858, then the pressure of our H2S goes up by that as well. All right, now equilibrium, we're just going to add those columns together. And so for the ammonia, I get 0.778. And for the H2S, I get 0.139. All right, now we're going to calculate K. All right, well, K is products divided by reactants. So the partial pressure of ammonia times the partial pressure of my H2S divided by, oh man, we have a solid, and the only thing that's a reactant there is a solid, so we just divide this thing by 1, right? And so now we're just going to plug in K is equal to, right, the values that we had. 0.778 times 0.139. And so the equilibrium constant for this is 0.108. All right, that's our final answer then. Well, here we're going to work another sample problem, and most of the problem we're going to find is going to be on the next slide. All right, but we have that, that methane and hydrogen sulfide gases are going to react together to form carbon disulfide and hydrogen gases, and it gives us some equilibrium concentrations of each one of them. All right, well, notice that these are equilibrium concentrations, right? But we're talking about gases. And so we got to think about that for a minute and see if that comes into play. All right, but the first one thing that it says to do is to write a balanced equation. All right, and so we are going to write a balanced equation for the formation of 1 mole of our carbon disulfide gas. Right, and so when we do that, right, we're going to get our balanced equation here. We need the balanced equation because we need those coefficients in order for us to use them in the solving of our equilibrium constant. All right, so let's flip over to the next page and see what it's going to ask us there. All right, but we're going to need these molarities in here somehow or another to work this problem. Here we're going to calculate Kp for the reaction. All right, so we could calculate the Kc from all the data that was given to us, or we can calculate the pressures of each gas and plug them into Kp directly, and that's the way that I've chosen to do it. Both ways will work. All right, but let's do the partial pressure first of our ammonia is equal to then nRT over V. And so let's plug in the values that we have here, which is 0.00142 moles times our 0.0821 liter atmospheres per mole Kelvin. And our temperature in this case was 1123 Kelvin. And we have a 1 liter volume. So we end up with 0.131 atmospheres. We could do the exact same calculations for each of the other gases that are present, and so I just already did those, and we'll write them out here. And then we can use these values and plug them into our equation for our equilibrium constant. So 0.869 atmospheres here. So our equilibrium constant in this case, products divided by reactants, is going to be the partial pressure of H2 to the 4th times the partial pressure of CS2 divided by the partial pressure of CH4, and finally the partial pressure of H2S squared. Just remember to plug in the values, and do not forget to, if you have to square something, square it. If you have to raise something to the fourth power, do that as well. Just make sure that you do all of those things when you do the calculations. So if we plug in all of our values and put them all correctly into our calculator, all right, finally I'm going to put in this one. We should end up with a K here of 333. Well, as we're approaching our equilibria, right, notice that this says that we are going to use the molar ratios to help us, determine how things are changing. Right, basically what that's saying is if you had, say, like A is reacting with 2 B's and coming to equilibria with, say, 3 C's or something like that, right, we can use those coefficients to know how much something is either increasing or decreasing by as we're approaching our equilibria. All right, now let's turn our attention to what in the world do the numbers of our K mean? Do big numbers mean anything? Do small numbers mean anything? So let's look at the magnitude or the size of our equilibria constant and what that's telling us about our reaction. So it says that reactions are feasible only if our K is large enough. So here I've got nitrogen and oxygen in equilibria with nitrogen monoxide. And notice that the K that is written down here is 1 times 10 to the minus 30. Small value. All right, what that tells us is that this reaction, yes, it is at equilibria, and yes, there is some nitrogen and some oxygen and some nitrogen monoxide. This happens. All right, but because that K is so small, that means that there are very few products. All right, so at equilibria, yeah, there's going to be a few nitrogen monoxides, but there's not going to be very many. It's going to be mostly nitrogen and oxygen. Well, just think about that, right? We are sitting here breathing in nitrogen and oxygen. If this reaction were taking place to a large extent, we wouldn't be breathing those in. We'd be breathing in a heck of a lot of nitrogen monoxide, which we're not. So that K value tells us a little bit about our reaction and which direction or which side favored in our equilibria. Now let's look at something like ammonia. Here I've got nitrogen and hydrogen. All right, so instead of nitrogen and oxygen, now we're going to turn our attention to nitrogen and hydrogen in equilibria with ammonia. Notice now, our equilibria constant for this is 6 times 10 to the 5th. This is large. This means that this reaction, when we reach equilibria, will have everything present. All things have to be there to be at equilibria. However, we're going to have mostly products. When we reach our equilibria. All right, so if we had nitrogen floating around our air and we pump some hydrogen in, we're going to get that ammonia smell because ammonia is going to be produced really quickly. So what that tells us then at the bottom, right, is that if our K is small, then we're going to have, right, mostly reactants. If our K is big, we're going to have mostly products. Right? Now, we're at equilibrium, so they all have to be there, but they just, again, equilibrium doesn't say that they're in equal amounts. It just means that the amounts don't change over time. All right, so that ends another podcast. And so we're going to then turn our attention to that Q that we kind of hinted at a little bit earlier called the reaction quotient. And if up to now you understand the equilibria constant, Q is going to be pretty straightforward.